Okay, so welcome everyone. Final day of HSMA training, which either will fill you with sadness or relief, or maybe a combination of the two. You've gone through a very intense course over the last 11 weeks, and we've shown you quite a lot of the, in fact, probably most of the things that we do. And so today we're going to finish with a couple of sessions this morning, looking at the final bit on natural language processing. And then this afternoon, Tom will take you through some cutting edge forecasting methods. But yeah, this morning we're going to talk about the other aspect of natural language processing. So on Tuesday, we talked about named entity recognition, which a number of you are going to be using for your projects to see if we can pull out named entity data automatically from free text data. But the other aspect, which a number of you are also doing in your projects, is to apply sentiment analysis, which is where essentially we're trying to determine whether what the tone is of a piece of text, to determine whether it's positive, negative, or neutral. And in fact, you know, some of the cutting-edge sentiment analysis stuff even looks at other aspects of tone beyond sort of simple positive and negative. But we're not going to go into that today, nor alas, are we going to talk about sarcasm detection, as much as I would love to do sarcasm detection, because I just think it's a lot of fun. There's a lot of research that's been poured into sarcasm detection, and nobody's actually got anywhere meaningful with it. Turns out it's very hard to do that kind of thing. But the same principles, as I'm going to show you this morning, essentially apply. Instead of trying to get it to learn that this is a positive piece of text, this is a negative piece of text, you would essentially just say this is a piece of sarcasm, this is not a piece of sarcasm. But as you can imagine, trying to get a machine to learn that when we as humans often fail to detect sarcasm is not easy. So we'll assume for the moment that the things we're going to be reviewing aren't too sarcastic, and hopefully this will work. So sentiment analysis. Now, hopefully you've all installed and got TensorFlow working. We'll soon find out this morning, and that you've downloaded this large movie review data set here. It's about 150 megabytes. There's actually 50,000 files just over in that data set, and it's basically taken from the Internet Movie Database, and it's a large collection of positive and negative reviews of movies, and trying to classify the sentiment of movie reviews is actually quite a standard way of trying to learn sentiment analysis. It's quite a nice way to do it. There's lots of data available that the IMDb make available for training on this kind of stuff. So if you've downloaded that, just make sure for the exercise that wherever you've put that is the same directory as your PI files for the session. So if I just show you, you should have, well, it'll be a zip file, but if you unzip it, you should have a folder that says ACL IMDb. Just make sure that's in the same folder as your these PI files that you've downloaded to. Okay, so sentiment analysis. We talked a bit about that in the first natural language processing session, and it's basically trying to use artificial intelligence-based methods so that we can identify the sentiment or tone of a piece of text. And sometimes you tend to classify that as positive, negative, or neutral. We'll talk a bit more about why that may not be helpful later and a way around that. But the most sort of basic method is essentially to say, is this text positive or negative? That's what we're going to look at first. And it works in a similar way to the way in which Spacey works. We talked about Spacey on Tuesday. Spacey's a really nice package, has lots of sort of parsing capabilities, and has really nice built-in named entity recognition, as we saw out of the box. It's performed really well. But of course, I said that underneath, Spacey is essentially just trying to predict whether a certain word or group of words is a named entity. And it uses a neural network to do that. And here we do the same thing. We're using a neural network to predict, to classify, just as you saw in Mike's course, can we classify that this piece of text is positive, this piece of text is negative? And we give it lots of training examples. We say, this is an example of a positive piece of text, this is an example of a negative piece of text. And our neural network will essentially look for those hidden patterns that might be difficult for us to see to form its own little, I would say rules, it's not even rules, it's weights of numbers, so that when it sees a new piece of text, it hopefully can classify it correctly. So there's lots of potential applications, sentiment analysis. Automatic classifying service user survey data is an obvious one, something we've done a little bit of before when we worked with Theraford, looking at their patient survey data. We can use it to analyze reviews of things like movies or books or whatever it may be. Analyzing social media posts. So one of the projects, HMA projects, going to do exactly that, looking at Twitter and seeing what people are saying about the organization and automatically classifying them as positive or negative. And can we identify what people are saying when they're saying positive or negative things? Can we do something about that? Or otherwise looking for positive or negative references to your organization on websites, etc. So very often your sentiment analysis, you're using it to identify the tone of what people are saying so that you can hopefully do something about it. So if people are, I mean, it works both ways. Hopefully you will also be looking at what people are saying positively about your organization, what you're getting right. But if there are common themes that are coming up that people are reacting negatively to, then hopefully that's something you can do something about. So the basic overall process for sentiment analysis is this, and you'll see, although it's by no means easy to do this, hopefully by now, when I start showing you the code, this won't look too unfamiliar, because you've started to see how we build up neural networks and the kind of basic processes we use for doing that. And sentiment analysis is very, very similar to that. The only difference is that we're using words, and I'll talk a bit about what we do about that in a moment. But basically, the basic process is we load in some raw text data, we clean up that data in some way, and again, I'll talk about that more in a moment. Now, the key difference here with natural language processing AI is, so computers fundamentally have to work with numbers, and that goes for neural networks too, because remember, all a neural network is basically doing is taking some numbers along connections that have weights, multiplying them together, then adding them all up, and then chucking them out the other side. Now, you can't do that with words, because obviously words are not numbers, and you can't multiply two words together. But what you can do is convert those words into numbers such that we can have a numerical representation for our words, and then we can feed them through a neural network. And I'll talk a bit about how we do that meaningfully a little later. Once we've converted it into numbers, we then convert it into a format usable by a neural network, which is basically, as we mentioned before, you put it into something called a tensor. I'm not going to go into detail about what a tensor is. If you want to suck up months of your life, you can. There's huge amounts of. There are books written on what tensors are. It basically comes from physics, and the easiest. All you need to understand is it's this format that's needed for these kind of neural networks, and they're basically, imagine like an abstraction of an array or a matrix. It's a tensor is kind of the abstraction of that. But please don't worry too much. I made the mistake once of trying to actually really get to grips with what a tensor is, and I wish I hadn't. So for the purposes of this, just imagine it as an array, but it's multi-dimensional, which makes it harder to visualize. So once we've got it in the format it needs, we then build our neural network up, and then we train the neural network by shoving all the training data through it, and then it gradually, hopefully, gets better and better. And then once we've got it fully trained, we'll then show it some data that it hasn't seen before, to predict, to see how well it predicts on this new data. So remember, we sort of hold back some data and say, you haven't seen this before, but I know what the answer is. Can you tell me, is this text positive or negative? And see if it gets it right. And that gives us an idea about how well our neural network can generalize, which is ultimately the point. It's very easy to train any neural network to get the training set right. But that's not very useful if it can't then generalize out to other things, because the whole point is we build something where it can predict things where we don't know the answer, and we want to be confident that it's doing that correctly. So let's start by talking about how we clean the data. So there's a number of things that we need to do if we're going to do sentiment analysis to clean up our text data. Now, this sort of stuff we don't tend to do so much when we're doing named entity recognition, and that's because things like whether something's got a capital letter or not, or words like and the, might be important to try to predict whether something is a named entity. But if we're trying to work out whether a piece of text is positive or negative, what we're trying to do is look at keywords. We're less interested about the kind of syntactic structure of the text, that this word follows this word, and then there's a punctuation mark here. Does that give us some clues? We're not interested in that. We're looking at keywords and trying to judge from those kind of keywords that are being used, is this indicative that it's positive or negative? So we actually want to clean up our text a little bit to make that process a bit easier. Because, for example, a word like and doesn't really help us determine whether something is positive or negative in any way. So we can do things like filter that kind of stuff out. So there's a number of things that we tend to do when we're doing sentiment analysis. First is we convert all the text to lowercase, because we don't care if someone wrote the word rubbish with a capital letter or with a lowercase starting letter, or even had a bizarre a range of capital and lowercase within the word. Doesn't matter. And of course, particularly when you're dealing with things that people have written online, or on a computer, on an online survey, maybe, they may well do things like that. There may well be little typos like that. That's okay. If somebody's written rubbish, we know they mean rubbish. We just want to classify that as the word rubbish. We don't care about how it's spelt. That's going to tell us nothing. We just need to know it's the word rubbish. That's the piece of information we need to help us to determine the sentiment. So we can do that really easily in Python. We can just tell it to cast everything to lowercase, and it'll just make everything lowercase. That just makes everything consistent then. We also want to tokenize the text. And tokenization is a word you'll hear quite a lot in natural language processing and in programming generally. It basically just means break strings down into individual words. You can also tokenize in sentence tokenize as well, which is where you break text down into sentences. But if we just say tokenize by default, we mean break some text down into individual words. And that'll allow us to then deal with those words separately. We also want to remove punctuation, because punctuation is rarely useful to determine sentiment. An exclamation mark possibly might help, although an exclamation mark on its own is not that useful, because it could be used to exclaim something positive or negative. So it's not really the punctuation that's helping us. So we tend to remove punctuation, and often we also remove numbers, because numbers don't often give us much clue about the sentiment of a piece of text, although they might. And we can leave those in, and if we're not sure, we could try it both ways and see if it helps if we leave numbers in. Depends on the context and what you're looking at. We also want to do something called stemming the words. So all that basically means is, let's imagine that we got 3 different reviews, and somebody said in one review watching, in another word watch, in another word watched. Well, they all have the same semantic meaning. They're all talking about the verb watch. It's just different tenses of that verb. And so we don't really want to have to treat those as 3 separate words that we have to train on and get it to recognize. It'd be far better if we could just say, okay, these are all talking about the watch verb. And we can do that using a process called stemming, and there are built-in abilities in Python that allow us to do that, to say, all of these words basically have the same meaning. They come from the same stem, which in this case would be watch. They have the same semantic stem, and so we can treat them all essentially as the same word. So it would, stemming here would basically convert all the words to watch, because it says the sentence doesn't have to make sense grammatically. It needs to make sense semantically, and so by converting them all to, okay, it's about the verb watch, that helps us. And another thing we often want to do is remove stop words. So I mentioned, words like the and a don't usually help us because they're on their own, they don't say anything about sentiment. So we can remove those words. What we're looking for is keywords that will give us some clues about how someone's feeling about something. So once we've cleaned up our data, then we need to somehow convert our words into numbers, because we're going to need to push numbers through our neural network. And remember, we're doing that because the neural networks ultimately need to multiply and add together numbers. So we need them to be in numerical form. And it's going to predict some numbers at the end. It's going to have outputs of that are numbers between 0 and 1, which indicate whether, if something's very close to 1, that we think it's likely positive. If something's very close to 0, we think it's likely negative. And if it's sort of bang in between them, it's probably quite uncertain. So the way we often do this for sentiment analysis is we represent our words according to the inverse of their frequency in the text. In other words, the most frequent words have the lowest number, so they'd have a number of 1. And the reason we do it like that is because if we think about what we're trying to do, we're trying to look for words that are commonly used. They will help us in our training. If we look at 100,000 reviews and one person has used one word that never comes up in another review, that's not going to be very helpful, because we haven't got much information to train on there. We've got one word, and that may be a positive or in a positive or negative review, but we're not going to be able to get much from that particular word. So we tend to just want to look at however many most frequent words we judge, and we can change that number. But if we have the words represented as numbers so that the lowest numbers represent the most frequent words, that allows us to easily chop out and set our threshold. So if we want to say, okay, we only want to look at the 10,000 most frequently used words, then we can set any words that have a number of more than 10,000, we can just remove them. So it makes it easy for us to determine what that threshold should be. So once we've converted them into numbers, we've now got to put them into a format that the neural network can understand, the tensor basically. And basically, this involves separating the data into inputs, which are the sequences of words, which remember are now numbers, which make up each bit of text you want to classify, and as labels. So we'll have so we've essentially got a series of numbers that now, so our review is now a series of numbers which represent words, and it'll have all the sort of stop words removed. They'll all be stemmed words, so words like watch and watching will be the same word. But that will essentially represent our review, and then our label will be a 1 or a 0 to say, given this combination of words, this is a positive review. Given this combination of words, this is a negative review. And typically 1 will represent positive, and 0 will indicate a negative review. We also need all of our inputs to be the same size. Whenever we chuck something through a neural network, everything that's passed through has to have the same dimensions. Now, with something like the kind of classification problems that Mike has shown you, that's easy, because you have a set of data. So in the Titanic example, you have a set of data about passengers, and you say you have 20 pieces of data, so 20 fields for each passenger. You'll always have those 20 fields. So maybe you have missing data, which Mike touched on, and then you do something about that missing data. But you always need to feed through 20 pieces of data. It's much easier to deal with. It's more difficult with text because, of course, not everybody writes exactly the same length of review. And even if they did, because we've cleaned up the data, removed things like stop words and done word stemming and things like that, even if everybody wrote exactly the same length, they would still be different lengths because people may have used more stop words than others, or use more words that got stemmed into other words. So there's no way we can control that. So the approach that we take is we decide on a size, a number of words that we think will give us enough information from a review. And then what we do is we say that's the maximum review size we want to look at. Anything longer than that, we chuck out the words beyond that. Anything shorter than that, so if we decide 500 words, anything longer than 500 words will be chopped. Anything shorter than 500 words, so say we've got 250 words, you then also have 250 padding words. And these are basically just dummy words with a value of 0. And the neural network essentially knows these aren't actually words. These are just padding that we use to pad out shorter reviews. Now, judging what the size should be is going to be a balancing act, because, and it goes back to the whole concept of AI, that it's always a balance between giving it lots and lots of data, which is potentially the natural instinct. But that's not always the best scenario, because you can run into problems of overfitting, that it learns patterns that aren't really there in if you were to look at everything, that they're just things about the training data that are unique to the training data. But then when you try and generalize it out to other data, that doesn't actually work very well. So there's a delicate balancing act between making sure you don't give it too much, but also that you give it enough that it can find these hidden patterns in the data. And as with all neural network stuff, this is a bit of experimentation. It's a trial and error. It's a bit of an art form that you see what works for your domain. You try out different sizes and see what kind of accuracy you're getting when you then apply your trained model to unseen data. And of course, the other thing that we need to do, which you've seen multiple times before now, is that we have to split our data up into training, well, at least training and testing sets, but we typically these days also want to have a validation set. So remember, the testing set is the bit of data that the neural network does not see during training. It doesn't see it at all. And it's just used so that after it's finished training and it now thinks it's ready, we can then try it on the testing set where we know the answers, and say, how do you predict this? And see how many it gets right. And that will give us an idea about, if we then take it on to brand new data where we don't know the answer, how good is it going to be? Validation data is similar, but it's part of the training set. So we carve off a bit of the training data and we use that for validation, so that as it learns, it learns on the training data, but it checks itself then against the validation data as it's learning, and says, okay, I did this well on the training data. I got 80% of them right by setting up this combination of weights. But when I look at the validation data, I only got about half of them right. So I need to reconfigure myself to try and get more of the validation right. So it tests itself using the validation data during training to try and improve itself. And then we test it with the testing data once it thinks it's got good enough. And that combination tends to work very well for neural networks, where you let them test themselves to improve during the training, and then we then test it on an unseen testing set. Now, it's important to note, whilst the neural network has access to the validation data to check itself, it cannot train based on that. So the validation data is not used for training. So it can't use those patterns of words, in this case, to update itself. It just sees, I only got 60% right. Therefore, I'll use that information. Where did I sort of go wrong? And I'll use that to try and update my weights, and I'll try again using my training data and see if I can get it better next time. So once we've done all that, we've got the data in the form we need. We've put it into numbers, we've cleaned up the text, put it into numbers, then we've put it into the format that we want. We've got a sort of maximum size, everything's the same length. We stuff it into a tensor, and then we can start building up the neural network. And remember, we often build these as sequential neural networks, which is basically just says, we'll build up the neural network one layer at a time. We say we want this kind of layer, and then we'll want this kind of layer, and then this kind of layer. And then once we've built it up, we then compile it to assemble it, basically. And then once we've done that, we then specify how many epochs. Now, remember, epochs are just the learning time unit. So basically, one epoch passes once all of the data, all of the training data has been shunted through once. So once all of the training data has gone through the network, remember we batch it up. So we don't, we rarely if ever would shove everything through at the same time, because that causes massive overfitting problems. We tend to batch it up into little samples of our data. Once we've shunted through all of the batches once, that then represents the epoch. So then how many times do we want to go through that process? How many times do we want to shunt through all the data? And again, that can be a bit of an art form, but I'll talk a little bit later about how you judge how many epochs you may need. Then once we've done that, we start the model training. So it's trying to learn the patterns in the training data, and it's using the validation data to try and gauge how well it's doing and try and improve itself. And we specify what output metrics we want, so we can judge how well it's learning. So what are we going to use to determine how good this thing, how well this thing is doing? So we're going to look at an example of exactly this, of how we're going to use sentiment analysis to automatically classify movie reviews from this movie review data. And obviously we're looking at movie reviews here, but the same principle applies regardless of what you're looking at. It just happens that we've got lots of movie reviews that are free and open source and readily available. And we're going to use Tensorflow for this. So those of you who've come along to Mike's first bit of the course will have seen him talk about TensorFlow. So there are two big platforms for neural networks that are used. One is TensorFlow, which is developed by Google, and the other is PyTorch, which those of you who came along yesterday afternoon will have seen Mike talk through PyTorch. So PyTorch used to be the big one. Google, being Google, have now eclipsed it in terms of popularity. TensorFlow is now the big one, but they do have advantages and disadvantages. So TensorFlow has something called Keras, which is an API that's been written to basically allow you to use TensorFlow more easily. Because if you were just trying to use TensorFlow raw, it's very complicated. So Keras is basically the thing we use so that we can write code that's a bit easier to understand, so that we can access TensorFlow underneath without having to worry about very complicated stuff. So it basically opens up TensorFlow to be used in a more mainstream fashion without having to have a degree in computer science or physics to understand what's going on underneath. And because of that, TensorFlow is relatively easy to use because of Keras. PyTorch is a little bit more fiddly because you have to specify everything. It does have the advantage, though, that because you have to specify everything, it's a bit clearer what you're doing. So if you're the kind of person that really likes to know exactly what's happening on every step, then PyTorch has got you covered because you have to declare everything about it, which makes it a little steeper learning curve. But then once you get to know it, it's a bit more friendly because you're kind of knowing what you're doing. Whereas TensorFlow hides a lot of that information. TensorFlow, though, is typically very good for sentiment analysis and is typically used for this. I'm going to show you TensorFlow, and also because it is ultimately easier to use as well. But this is the standard method for that. TensorFlow is less good when you're not shoving through, when you're dealing with sort of small bits, pockets of data, such as you are using in reinforcement learning, where you're learning a little bit of something, and then you're trying to improve, and then you're learning a little bit of something, and then and that's why Mike uses PyTorch for reinforcement learning stuff. But for this kind of stuff, we'll use TensorFlow. So you've seen a bit of TensorFlow before, but I'm gonna assume that you've forgotten or didn't understand it, and we'll go through it as though you haven't. And before I show you the code, let's just remind ourselves of all the bits that are important here, and essentially what this code is doing. So the first thing that we're going to do in this code is we're going to set up a directory structure for our text. And we do this because there's a really nice package built into TensorFlow that also into Keras that allows us to automatically read in data as both positive and negative examples of text if it's been saved in this particular structure. So we can have a folder that says test and a folder that says train. And one obviously will hold our testing examples, one our training examples. And then we can have subdirectories in each of those for each of the categories that we want. So in our case, we're doing sentiment analysis, so we want negative and positive categories. We might have neutral as well, but we're not worrying about that. So essentially, if I show you the directory structure, so the data set you downloaded, if we go into it, ignore this bit, which is just some information, you'll see there's a test folder and a train folder. So if I go into the train folder, this is our training data, and you can see that's been separated into neg and pos folders. So then if we go into neg, just give it a moment to load up, so there'll be thousands and thousands of negative reviews here. And they're just text files. These are just text files of negative reviews that we can use for training. So I'll just click open the first one. Story of a man who has unnatural feelings for a pig. Okay, I don't know what I've opened there. But you get the idea. Basically, you've got all of these reviews that are separated into training and test, and then within that, negative and positive. And if we separate our data up in that way, then it makes it really easy to then load that stuff in, because there's this great utility, which I'll show you, where in a single line of code, you can basically just say, there's my data. And as long as it's in that format, it'll then automatically work out, okay, so those text files are for label negative, those text files are for label positive, and that's my test set. And it does all of the hard work for us. It's really, for the sake of us, essentially just putting it into the correct folders makes life a lot easier for us. It's a really nice utility. So then once we've done that, we're going to split it into our, we've got our training and testing sets split because we've read it in from this data. But what we will need to do is, if we haven't gotten a separate validation set, which we haven't in this data, then we'll need to carve off a bit of our training data and tell TensorFlow, hold this back, don't train on this bit. Use that to fine tune yourself during training. Use that as your validation set. And we can do that again, single line of code, just say, carve off 20% of the training set, and I want that to be your validation set, and it'll do that. It knows what you mean by that. Then we're going to do our what's known as standardization, vectorization, and embedding, which sounds very fancy, but it's basically what I've just been talking about. So the standardization is basically the cleaning up of our text. So the first thing we're going to do, because these reviews have come from the web, they have HTML tags in them. So we're going to need to clean those up. Now, if your data hasn't come from the web, you won't need to do that bit. But because you're working with web-based data, then it's going to have HTML tags. And so we can remove those, and there's easy ways we can do that, which I'll show you. So we remove the HTML tags, and then we'll make everything lowercase here. So we'll remove the capital letters, and then we'll remove the punctuation. And then once we've done all that, that's our standardization, where we've cleaned up the text. We're then going to what's known as vectorize the text. And basically, that just means what I was talking about earlier, turn the text into numbers. So that's the bit that will say, this word translates into this number. I should have said, actually, sorry, that's for example, because the word "the" would have also been removed here because it's a stop word. But essentially, so each word will be given a number, which will be the inverse of its frequency in the data set. And so each word will be, across all reviews, will be given a number, so that the same word "movie" will always have the same number across all of the reviews. And that the vectorization will do that process for us and turn it into basically a vector of numbers. And then we'll do the last bit, which is the embedding, which is just the fancy way of saying, and then stuff it into a tensor, chop off words that are sequences that are longer than this, pad out sequences that are shorter than this, and then stuff it into the shape that we need to shunt it through the network. That's basically the embedding bit. So we standardize, where we clean up the text. We then vectorize, where we turn the text into numbers, the cleaned up text, and then we embed to get it ready for the neural network. So reminder, this is then the neural network that we'll build. And basically we'll have a series of layers. We'll have an input layer, which is where the tensor gets fed into, and then a series of hidden layers, which is just basically ways of saying the ones in the middle, and then an output layer. And all of the neurons in the middle are basically doing all the magic for us. And we'll also have some dropout layers in there. Remember, we talked about dropout the other day, which is where we said it's really useful in neural networks to have dropout, which is where essentially you turn a random portion of these off at every training iteration. And it's common to have that quite high, about 50%. So you say every time you run through, randomly switch off half of these, and it prevents overfitting. It prevents us getting the network. Otherwise, will get too. It'll learn too much about the training data, but it'll learn stuff that is just unique to the training data. So it'll learn the training data superbly. You can get 100% accuracy sometimes, but then it'll be really poor at training anything else because all it's done is just learn the things that are unique to this pattern of words in the data it's seen. It hasn't learned the more general patterns, which is what we're trying to get it to do. And remember, each of these nodes, so this is an example of a densely connected network. That just means that all of the nodes in each layer are connected to all of the nodes in the next layer. And each of these nodes is basically doing an activation, which is essentially where it multiplies. So show you on the next slide, be a bit easier to see. So we've got all of these incoming signals. So your numbers that are being chucked out by the previous layer are coming down our signal, our synaptic connections, our links. Each of those links has a weight associated with it, and these are the things that the neural network is going to play about with to try and get better. So let's say the number 3, let's say we have 3 connections coming to this neuron. The number 3 is coming down here, the number 6 across here, the number 2 across here. And let's say that the weights at the moment for this for these connections are 0.5 here, 0.1 here, and 0.2 here. So all the activation in the neuron will do is say, okay, so I'll times 3 by 0.5, I'll times 6 by 0.1, and I'll times 2 by 0.2, and I'll add all those numbers up, and I'll get a value of 2.5. And then it shunts that number out the other side. That's all a neural network is doing, essentially. But then it gets better by changing around these numbers, because remember, these numbers represent words. So essentially, it's weighting certain words more highly than others. It's not quite as simple as that because there's other sort of hidden patterns, but that's essentially what it's doing at the simplest level. It's changing around these weights such that when it gets a certain combination of numbers come in one side of the network, which are for a positive review, that it's getting a number of 1 or close to 1 that comes out the other side. So how do I change around my weights such that I can get these numbers, for example, to come out to the number of 1? But of course, it's very easy to do that for one single example, but I need to learn how to do that for thousands and thousands of examples, so that I use the same weights, so that when those numbers get passed through, I get the right result. And that's the magic of neural networks, basically. So that's what it's going to do. Let's now look at the code to see how we code that. Sorry, before I go on, any questions about any of that so far? Okay, so let's look at the code. First thing we're going to do, as you know well by now, is to import the stuff we need. So the stuff I'm importing here, I'm importing a library called RE. We're just going to use that to do some regular expression stuff. That's for the HTML tags. You'll see that in a bit. I mean, I don't like regular expressions, so I'm not going to go into too much detail about that, but just know that we use that for this. We'll also import the string library. The string library is quite a useful library if you're dealing with text, because it has lots of useful functions that you can do on strings. And I think we've seen a couple of those examples maybe in some of the previous sessions, but it's a useful little library, and we can use a couple of bits in this. We're then going to import TensorFlow. So we import TensorFlow, and as with pandas and NumPy and matplotlib, there's a standard alias that we use. For TensorFlow, that's TF. So we import TensorFlow as TF, and we can refer to TF now throughout the code to refer to TensorFlow. And then, because we don't want to work with TensorFlow raw, because it's very complicated, we then import some stuff from Keras, which is the friendly layer that goes on top of TensorFlow that allows us to write simpler code to do the TensorFlow stuff that we want to do. So we're going to import some various things here. We're going to import the idea of layers, losses, pre-processing, and something called text vectorization, which, as I've just shown you back here, is the bit that's going to do the magic where it converts our text into numbers. So there's a package that allows us to do that. So let's start with the code itself. So remember, as I've said, when we build a neural network, we would almost never push everything through the network at once, because it leads to overfitting. So you tend to batch up your training into little batches and then shunt it through a batch at a time. And a good initial batch size is 32. So in this case, it'd be 32 reviews that are going through at a time. Again, that's a bit of an art form, and it will something you may want to play around with if you're building one of these. But 32, that kind of area tends to be quite good for this kind of thing. We're also going to use something known as a random number seed. So we've sort of alluded to this a few times in the course, but it may blow your minds to know that when you tell Python that you want a random number, so let's say you've imported the random library and you get it to tell you a random number, that number isn't actually random. It's what's known as pseudo-random. It fakes randomness. And it does that through a very complex algorithm that uses your combination of your processor and the current time to generate a what appears to be a random number, but actually isn't. It's just an algorithm that's happening in the background. And you can prove that by using what's known as a random number seed, because a random number seed is basically a way of telling it, yeah, I want those random numbers over there. And so if you give a random number seed and then you ask for random numbers with that seed, you'll all have exactly the same random numbers. So they're not actually truly random. Now, that is not, unless you're the sort of person that stays awake at night thinking, but it's not truly random, then don't ever worry about that again in your life. It's not a problem. All computers do this. It's just the way it works. You can get truly random numbers, but you have to do things like measure radioactive decay to get true randomly generated numbers. You can buy them. There are services online that if you think, no, truly random numbers are the only thing that will do for my model, then knock yourself out and buy some radioactive decay generated random numbers, and you can use those. But I'd recommend you probably might want to think about that. But basically for this, we're going to use a random number seed, not only because it's quite useful for training, but also because it's actually essential when we're going to do what we're going to do, which is where we've got a set of training data, and then we're going to carve off a percentage of that training data for our validation data, but then we're going to shuffle everything around. So we have to make sure that there's no additional shuffling, because randomness would bring in shuffling, so that we don't accidentally mix up the training and the validation data. So you set a random seed so that basically you make sure that every time it runs through, it'll only shuffle the training data in place, but it won't. We won't end up dipping into the validation data, which it's allowed to look at during training, but it's not allowed to use that for training. So don't worry too much about that. Just know that's the reason why we have a random seed in here. So now we're going to start reading in our data, and we're going to use this. I alluded to the fact that there's this nice utility that allows us to basically automatically read in our data without us having to go through lots of manual processes if it's been stored nicely in that directory structure that I outlined. So having a train folder and a test folder, etc. And this is the thing we import at the start, this text data set from directory in pre-processing. So we imported the pre-processing module up here. One of the reasons we did that is because it also has this thing called text data set for directory. And this basically does the magic for us. So we can just give it, here's our directory, which is ACL IMDb, show you there. So we think that's the directory, and if I'm talking about the training set, it's in here. And then it'll do it for us. It'll automatically, we don't have to go through and read all 50,000 files manually. It'll do all this for us. It'll say, okay, I know where the training data is now. So here we're telling it that's where it is. We need to tell it, so here basically we're setting up our training data. So this is going to be our training data set, and I've called it raw train DS, raw training data set. And I've said I'm using this text data set from directory to say it's stored in here. The batch size that I want you to use when you shut this through the network is whatever I've set my batch size to, which is up here, 32. I'm going to set my validation split to 0.2. So because we're using this this Keras utility, it basically allows us to say we don't have to specify and manually carve off 20%. We just say 20% of that training data I want you to hold back for validation. So just that single line here will do that for us. It knows what we mean by that. So we can just say the validation is 20% of this data, and it'll carve that off for us. The subset I'm talking about here that I want stored in raw train DS is the training subset. So this is going to be our training data. And the random seed, which I explained above, is just whatever we set it to, which was 42. The seed is that. So that then sets up our training data. So let me run this first bit, and you can see how this is working. So if I run up to here for a moment, and it's thrown up an error, that's helpful. Sorry, bear with me one moment. Oh, I know why. I haven't set my working directory. So you may run into this, but this is actually quite worth flagging up. You haven't had to set your working directory very often in Python. And that's because when you run the an entire program by hitting F5 or hitting the play button, it will automatically set your working directory to wherever this file is located. So because this file is located in the directory I need, that wouldn't have thrown up an error. But if you're just running a bit of the code and you haven't yet run the full program, it won't do that. And so you'll see my working directory is actually set to the wrong directory here. So if you need to set your working directory manually in Spyder, just use this little folder icon up here, and then you can say which folder, which working directory you want to look at. So in this case, it will be 11C, and then Git, and then here. I'll use that one. That should now work, fingers crossed. Okay, that's brilliant. Okay, that's worked. Don't worry about all this. This is, you get a load of warning messages from TensorFlow. Ignore them. Just don't worry about that for a minute. So what we've done so far is we've just done this bit. We've done the imports, we've set up the batch size and the seed, and we've set up our training data set. So what it's done is it's read that into this variable called raw train ds. Now, to see the magic of how this has worked, how it's automatically read in that some of it's positive and some of it's negative, we can print the class names that is automatically assigned. Because it should have automatically assigned one of the labels to 0 and one of the labels to 1. So let's see what it's done. So I can print that label 0 corresponds to, and then I can access the class names of my data set and say whatever 0 is and whatever 1 is. So let's see what it's done. So we run that. There we go. So it's picked up, it's automatically assigned that label 0 corresponds to neg and label 1 corresponds to pos. So in other words, in the training data here, it's read in these two folders, and it said that all of the stuff in here, in neg, it will have a label of 0 for training, and all the stuff in here, in pos, will have a label of 1 for training. So 0 is our neg, and 1 is our pos. That's good, that's what we want. So we've set up the training set, we're happy that that's read in correctly. So the next thing we're going to do is set up our validation set, which remember is just we've carved off 20% of our training set to be our validation set. So we set this up in exactly the same way as the training set. I've just called it raw val ds for raw validation data set. I tell it where it is, and again, it's the training folder because it's part of the training set. I give it the batch size. I again specify that it's the 0.2 of the validation split, so 20% of this. But this time, so it's exactly as it was up here. The only difference is that I say, now I'm talking about the validation bit. So that 20% that you're carving off in here, that's the bit that I want you to store in this one, which is the validation set. So now we've got the training set stored up here, which is 80% of the training data, and the validation set down here, which is the 20% that it's carved off. Okay, so that does all the magic for us. We don't have to worry about manually doing that. And then the last thing we need to set up is the test set. We've got the training and the validation sets. So now let's set up our test set. We're just going to use the test set as is. We don't need to split that up in any way. It's already in a test folder, so we can just do this really simply. I'm going to store that in raw test ds for raw test data set. And all I need to pass into this is just the folder, which is the test folder, and the batch size. I don't need to worry about the seed because that we don't shuffle around the testing set because we only do that for training. So this is just the data we're going to show it after to see how well it's trained. So we just tell it where it is and the batch size. That's all we need to do for the test set. So we then need to think about how we're going to clean up our data. So remember, we need to standardize our text data to clean it up, remove punctuation and do all that kind of stuff. And because it's IMDb data as well, we need to get rid of some of the HTML tags that are in the raw text. So basically what we're going to do is we set up a function so that we can call that on whatever data, and that will do that for us whenever we call that function. So just call it custom standardization here, accepts an input of whatever the input data is we want to clean up. The first thing this is going to do is convert everything to lowercase. And this is where we use the string library, the strings library of TensorFlow, which has this method called lower, which basically, if you pass in some text, it'll convert that text into lowercase. So everything will be lowercase. And then we store that in lowercase. So now we've got in lowercase, whatever data we passed in, text data, but now it's all lowercase. Then we're going to strip out the HTML tags. We only need to strip out the line break tag for this, but the same principle would apply if you had other HTML that you had to strip out. And we do this using the regular expressions. Don't worry too much about what this is doing, other than it's using this method called Regex Replace. Basically using regular expressions to look through the text and remove the line break. So what this is saying is, take in lowercase, which is our text converted to lowercase, and find that, which is the line break tags, and replace it with that, nothing. Okay, so that will remove that for us. So now we've got our text that has been converted to lowercase and stripped of HTML. And the last thing we're going to do in this one is basically just to remove the punctuation from the lowercase stripped text, and then return it. And we do that as we return it. So in this return statement, we're basically saying the last thing I want to do is return this stripped HTML, but I want you to, on the way out, also get rid of the punctuation. Don't worry too. I really don't want to talk about regular expressions because they're horrible. This line of code will do it for you. It basically just says look for punctuations. In fact, if I show you, let's have a look. I've imported string. So if I show you, if I type string.punctuation, let's import it. Here we go. So this string library that we imported up here, I said it's quite useful. One of the things the string library has is a list of punctuation marks, which doesn't sound very exciting, but it's really useful for us here because we can say all of those things, which if I print string.punctuation, it's this. Anything you see in the text that's got that, remove it. So replace that, these things here, with nothingness. Don't worry about this. This is the regular expression bit, which I don't want to go into, but that's basically what it's doing. Okay. So we've converted everything to lowercase. We've stripped out the HTML, and then we finally remove all the punctuation, and then we return it back. So we've cleaned up our text. Oh, sorry, no, we haven't. We've defined a function that will clean up a text, so that when we're ready, we can call that function on our data. The next thing we're going to do is we're going to set up a text vectorization layer ready for when we build our neural network. Now, remember, the vectorization is the process of converting our text into numbers. The way we're going to do it here is we're going to set up a little miniature neural network layer that does that. And it's this little standalone layer so that we can feed in text and out the other side will pop numbers. That's basically what it's going to do. So in preparation for that, we're also going to set up the other stuff that we're going to need to do. And that is we're going to store a maximum number of features. This is the maximum number of most common words that we want. So remember, the way it's going to vectorize, turn the text into numbers, is by doing the inverse of the frequency. So the number 1 will represent the word that is most commonly used. So if we say maximum features 10,000, then we'll only take the 10,000 most common words, and only those will be used in the reviews for training. And the sequence length is what we were talking about before, which is the maximum number of words in a review in this case. So any reviews that are longer than 250 words will cut anything beyond the 250 words. Remember, it's not 250 words of the initial review, it's 250 cleaned up words. So you may have a 500-word review, but by the time you've taken out the stop words and stemmed the words and done all that sort of cleanup, it won't be 250 or 500 words. It'll be much fewer than that. So you're actually having reviews that are slightly longer than that. But again, this is something you play around with. So we're going to set it to 250. And then we're going to set up our vectorized layer, which is going to do the magic for us. And we're going to set that up as a text vectorization. Remember, that was the magic we imported at the start up here. This import text vectorization, that will do all the hard work for us, so we don't have to tell it what to do. And we just need to pass it 4 things. How we want the text to be standardized, i.e. how we want it cleaned up. Well, we've written a function here that tells it how to do that. So it'll basically call that function. It'll say, use that function to clean up the text first. The maximum number of tokens is just the maximum features. In other words, the 10,000 most common words that we want to use. Output mode is basically just saying how do I want my numbers how do I want my words to be represented, and int just means turn each token into an integer, which is the most common way you do this. And the output sequence length is the sequence length we specified up here. So in other words, no sequences of words more than 250. So that sets up the layer and says when we use that layer, then clean up the text using this function we've defined above, and only take the 10,000 most common words, convert them into numbers, and we only want up to 250 cleaned up words per article per review. So then we're going to start the process of mapping our text into numbers. We first just want to extract just the review text, i.e. not the labels as well. So just the review, not whether it's positive or negative, so that we can make a text-only data set. Now, we do this using something called a Lambda function. You won't have seen these before. Don't worry too much about them. They're basically, think of a Lambda function as like a little mini function in Python that's anonymous. And in other words, we don't give it a name. It has no name. We just immediately declare it in this little line of code. We use it, and then we chuck it away. We don't use it again. So it's a bit odd because we've always talked to you about functions as being these things. The whole reason of writing a function is that you declare a function with a name, and then you can use that function to do the same thing time and time again. This is kind of the opposite. A Lambda function is kind of the opposite. You just want it to do something very quickly once, and then you'll chuck it away. You don't need it again. So what this says is basically, give me X and Y as the inputs and return X. In other words, give me the text and the labels, whether it's positive or negative, and just give me back the text. And rather than write a few lines of code to do that, we can just say here, I want you to do this little mini function that takes those two things and just gives me back the text. And we can apply that to the raw training data set to just give me the text. Once I've just got the text, I can then feed that in to the vectorized layer to get it to adapt, because what it's going to do is basically these two lines of code, basically what they're doing is they're taking all of the training data, they're looking at all of the words that are used, cleaning it all up, and then, so as we defined up here, and then taking the 10,000 most common, and then converting those words into numbers so that the same numbers are used throughout the training data to represent the same words. So basically, give me back the text, then shunt it through this vectorized layer, and then we've got our training text is now adapted, ready for this to happen. So once it's been adapted, we can then apply this vectorization layer to actually get it to do this. And we'll create a little mini function that does that, which takes as input text, the review text and the label. And then we'll essentially apply the vectorization layer. This extra line of code here basically takes the text and it reshapes the tensor so that it can be fed through this thing up here. Again, don't worry about that, just know you have to do that. It basically changes the shape of this tensor so that it can be fed through. You only have to do that because we've set up this separate little layer here. Normally you do all that as part of your neural network. But basically this function is going to say, so here we've got everything ready and adapted. We've adapted the training data ready to go through, and this function will then reshape that tensor, and then it will run this function on the text. Sorry, not this function, this layer. It'll apply this layer to our training text, and then in turn that will call, as its first step, call this, which will clean up the data. So essentially it will take the training text, we've adapted it, ready to go in. Now it's gone in, and we clean up the data. It'll clean up the data for us and convert it all to numbers as we want. now we've done that, and we've adapted the pre-processing layer, the vectorized layer, to deal with the integer representations of our text strings. We'll now apply it to the 3 training sets, and we're going to store them as 3 new data sets. So we'll still have our raw data sets as they are. We want to keep those as they are, which are as sequences of strings, basically. So that will be our raw reviews before they've been cleaned up and turned into numbers. But then we're going to use the map on the vectorized text to say, given this mapping that you've now worked out for assign this word to this number, make that happen for the training set, the validation set, and the test set, so they all get converted into numbers. And we'll store these in these separate sets here. So train DS, val DS, test DS. These are the ones that we're going to have to use in our neural network because these are now numbers. But we'll keep these raw ones. These are these strings of reviews because we may want to refer to those later. So here we'll basically convert our 3 training sets from words into numbers, and we've done a few little extra things up here to get it ready for that. So once we've got everything prepped, we can now just build our neural network. And remember, this is sequential, so we're going to build it up layer by layer. The first layer is going to be the embedding layer. That's the one that gets it into the format we need, chunks it through in the correct format. We're going to use an untrained embedding layer, which is the easiest way to do this. You can, though, also use what's known as a pre-trained embedding layer, which has been trained on common words. So if you came along on Tuesday, you remember we talked about the advantage of transfer learning, which is where basically we start not with a brand new out-of-the-box blank canvas model. We start with a model that's been pre-trained on lots of stuff, so that we don't have to worry about all of the training on all of the common words from scratch. So you can do that here as well. And if you want to do that, I've added a link to some more information on it, and also some code that you would use to do this. So if you uncomment that bit of code and use that instead, then it will use this pre-trained embedding layer at the start. So you'll start off with some pre-training. I'm not going to do that now, just to keep it simple, but I've added that in there so you can see what difference that might make. It may make no difference to your particular problem, but it might help because it essentially gives it a leg up on the training. So we'll start off with that embedding layer. Then we'll have a dropout layer. So in this case, we're going to drop out 20% of our, we're going to switch off 20% of our neurons on any particular training run, training pass. Then we're going to have something called a global average pooling 1D layer. Again, don't worry too much about what that is. Basically, what it does is it squashes down the tensor by removing dimensions, making it all one-dimensional. So it takes pooled averages basically to do that. They tend to be used to prevent overfitting, because if you've got less data, then there's less potential to overfit. That's basically the principle of how it works. So you squash everything down. And again, as with all neural network, lots of people have done these sort of things before and found out sort of combinations that tend to work quite well. But the advantage of building any neural network here is you can play around with it. You can put in your own layers, there's lots of layers you can choose from to see what works best for what you're trying to do. So we've got the embedding layer, which gets it in the shape we want. Then we've got, incidentally, sorry, I didn't mention this. You're maybe wondering why we've passed in max features, which, if you remember, is we said is 10,000. So that's basically there'll be 10,000, the 10,000 most common words. If you're wondering why it says +1, it's because there is an extra word 0, which, remember, we said is the padding word. So any reviews that are shorter than 250 words, we need to pad them out with the word 0, which is a dummy word. And so that's why we're actually passing in 10,001 features here. So after the global average pooling 1D layer, we'll have another dropout layer, and then we'll have a densely connected output layer, which just means everything is connected into it. But it'll have a single output node. So that basically, that final node will output a number that will be between 0 and 1, and that will determine the probability of whether something is positive or negative. So let's run all this and have a look at the summary of the model. So where did I run up to before? There. Okay, so it's up to that. So let's run this bit. He's not. Oh, it's because I have to do everything again. Sorry. Okay. Let's give that a moment. There we go. Right. So now what we've done is we've set up the neural network. We've set up all our text ready. We've built the neural network. We haven't done anything with it yet. But what I have done is just to ask it to print a model.summary. Now that's a really useful thing that you can do that basically summarizes, that's the model, the neural network we've built. So we've got an embedding layer, we've got a dropout layer, and then this global average squashy layer, and then another dropout layer, and then a densely connected final layer. That's our 5-layer model neural network. Okay, so it allows you just to make sure that you're happy with the neural network shape you've done. Now we've built it, we compile it to assemble the whole thing. And this will look very familiar from the other neural network sessions. We use model.compile and we specify an optimizer. Remember, the optimizer is the algorithm that changes the values of the neural networks, such as the weights and learning rate, to reduce losses over time. And remember Mike's comments, if in doubt, pick Adam. Adam is now the most commonly used optimizer. So optimizer equals Adam is probably what you would use virtually all the time now. We also need to specify the loss function. Remember, the loss function is the thing that will calculate the difference between the result the neural network predicts and the actual correct answer. And for those of you that yesterday, Mike again mentioned that we tend to use a binary cross entropy loss function where we're trying to predict a classification problem because they're good at dealing with probability. So in other words, I've got 2 potential classifications, positive or negative. What's the probability that it's positive? So binary cross entropy is very good at that because it measures the distance between probability distributions is the technical reason. But rule of thumb, if you're trying to classify in 2 different categories there, you'd use a binary cross entropy, and that's good. From logits equal true just basically means normalize the outputs on that final output layer so they're between 0 and 1. If we didn't do that, then essentially we could have any number between negative and positive infinity come out the other side. So we want to normalize that to make sense of it. So we'll make sure that all the outputs are between 0 and 1, and that will give us a sense if it's close to 1, then it's probably positive. If it's close to 0, it's probably negative. And then finally, we specify the metrics. So how will we judge success, and how will the neural network determine how successful it's being? We're going to use accuracy, which is just the number of predictions the machine got correct out of the total number of predictions. So that's how it'll judge how well it's doing and how well we'll judge it as well. So once we've built it, we compiled it, let's start training it. And basically this does everything. So we're going to train the model. Remember, in neural network terms, training a model is known as fitting. So when we tell it to fit the model, it means train it. Now go off, use the training data and train yourself. We store the results of training. You don't have to do this. You could just call model.fit with all this. But you normally would want to store the history. And the reason we do that is then we can interrogate it and ask questions about it. We've got a record of how it trained. So we usually store that in a variable called history. We've specified we want 10 epochs. Remember that an epoch is the amount of training time for all of the data to be shunted through once. So we now tell it to fit, i.e. to train. We give it the training data set we want. That's train DS. That's the one up here that we converted into numbers using our vectorization layer. We give it the validation data set as being val DS, which again we did up there, converted it into numbers. That's 20% of the training set. Number of epochs is is number of epochs, which is specified here. That is 10. And verbose equals 1 just means tell me everything you're doing as we go through. So you can see what it's doing and how well it's performing during the training. If you set it to 0, you won't see anything until it's finished. And if you set it to 2, then it'll tell you everything, but it won't show you a little progress bar. So it's usually verbose equals 1, especially when you're setting this up for the first time. You tend to want to have it verbose. You can see what it's doing. So once we've trained it, we can then evaluate the model to see how well it performs on the test set. Remember, it hasn't seen the test set. It hasn't been trained on that at all. And it's seen the bit of the training set that we kept separate to test itself. But now we're going to test it on data it's never seen, but where we can tell it the answer, so it can judge how well it does by using its rules to try and predict. So let us now run this. So that, I'll come back to those last 2 bits in a moment. Let's run the whole thing now. Okay, so it's loaded in all our training data here. Now it's going to start training. So it's gone through epoch 1 and then epoch 2. Now, note, I don't know how well you'll be able to see that. Sorry, I can't make this any bigger, but the you'll see over here it's measuring as we go along the loss and the accuracy. Remember, lower loss is better because it means you're closer to what the actual answer was, and higher accuracy is better because it means you're getting more of them right. And you can see that loss seems to be going down very well. Accuracy is going up. We're up to 91% already. That's really good. But there's also validation loss and validation accuracy here as well. And that basically is, remember, it's really easy to get very good at predicting the training set. It's much harder to then generalize that out. So validation gives us some sense about how well it might be doing. So if we look here at epoch, the final epoch, epoch 10, we got up to 91% accuracy. So it managed to set it to train itself so that it got 91% of them right. It correctly classified 91% of the training examples as being positive or negative and got them right. And it had a relatively low level of loss. But when it checked itself against the validation data, that's much lower. It's only 87% accuracy on the validation data. So that gives us an indication that it may, when we then give it brand new data that's never seen at all, it might not be quite as good. And indeed, that's what's happened. So then when we've trained it, we then evaluate it on the test data set and we get it to print out the loss and the accuracy. So that's what we did here. So this model.evaluate, after we trained it, we can pass in a data set to say, now test yourself on that. Try and predict this. Here are the answers. How well do you do? And it'll test itself. And here it's picked up. So it's got 86% of them right, basically, which isn't bad. It's pretty good. So it's managed to, on brand new data that it's not seen on review data, it gets 86% of them right, which is pretty good. But there may be ways in which we can improve that even further. So the last 2 bits down here are just that if we want the model to be able to process new raw strings of text, in other words, we want to use this model, our trained model, for new data, which is the whole point. We don't want to have to go through that rigmarole at the start of having to vectorize the, set up the vectors so that we convert it all into numbers and do all that manually each time. What would be better is if we basically save a new version of the model that not only has all of the stuff we've set up here, so our 5 layers, but we bung on another couple of layers. So that vectorization layer that we set up at the start that does all the magic around converting text to numbers, let's bung that on at the start of the neural network. So then we can just feed the text into the neural network and it'll do all the magic for us. And then at the end, we'll bung on a sigmoid activation function so that we can automatically get a value between 0 and 1. So a sigmoid activation function will basically return a floating point number between 0 and 1. So we don't have to do what we did before, which was try and normalize the numbers here in the cross entropy function. Instead, we can just say, have a final layer that takes the penultimate output and then just converts that number to between 0 and 1, and that will represent our probability. So basically, our new model will be the vectorized layer that we set up right at the start, which does all the magic of converting text to numbers. Then the model that we've just trained, and then the an activation layer that will then convert the output into a number between 0 and 1, and that will be our new neural network. It'll be made up of the 5 layers we've just read above, but at the start we'll have a vectorization layer, and at the end we'll have a sigmoid layer, activation function layer that will convert that into a probability, so that if the neural network comes out with a number 0.7, that means something to us, because we can say, oh, okay, that looks like it might be veering towards this being a positive review because it's close to 1. So that will be, we can then interpret those results. And then we can just compile that model, and exactly as we did before, except this time I set from logits to false, because we don't now need to normalize it in the loss function here. We can just, because we've got a sigmoid activation function, that will give us a number between 0 and 1 at the end for us, and that's a better way of doing it. So we've now got a brand new model that we can use. We can just shunt in raw text, and it'll convert it into numbers for us, and then it'll train on those on that text, and then it'll spit out a probability between 0 and 1 at the other end. And we can also then use that exported model here. So when we called in the model bit here, that's now the trained model, because we've trained it up above. So now if we want to use that trained model, we can, on brand new text, so let's say I want to now give it a review and say, do you think this is positive or negative? I can just feed that in directly to the network, and it'll use this pre-trained stuff in the middle, along with the vectorization layer at the start, which will turn my text into numbers, and then the output layer, the sigmoid layer at the end, which will convert that to a probability that I can understand. Okay. Any questions about any of that? I realize that's quite a lot to take in, but you'll see that the process is identical whenever you go through this.
Dan, I thought I'd followed your instructions, but something hasn't worked for downloading some of the stuff. So I whichever group you put me in is going to have somebody that's already managed to get it to work. Download.
Okay. Yeah, no worries. I'm sure.
I don't know why it didn't work, but until you start using it, you don't know what you're expecting from it. So
yeah, no, absolutely, no, that's fine. I'm going to make the groups a little larger anyway, because actually the exercises I'm going to get you to do today are less about the coding. So you're going to have to do a little bit of coding, but the coding is actually quite easy. It's I want you to explore the model. That's the more interesting part. So just one last little bit I'm just going to talk about before we take a break and then you move into the exercise. So we talked about overfitting. Now, if we saw before, when we looked at the training of this model, that the training loss was decreasing and training accuracy was increasing very well. But if we look back at the validation loss and accuracy, that seems to peak early and not get any better. So have a look. If we get to around epoch 4, we're up to about 83%. Sorry, this one here. Up to about 83% on the validation set. Next epoch, we get up to about 85%. Then it stays about 85%, goes on a little bit to 86, a little bit to 87, but it's not getting much better compared to the training set, which is jumping up quite a bit and getting up to 91%. Now that is an indication that we're maybe starting to overfit. In other words, we're running into diminishing returns. We've learned everything we need to from the training set that we can then use to generalize. And if we go too much further, we're just going to end up learning stuff that's just unique to the training set, and then it'll be rubbish at trying to generalize to anything else. So that's a warning sign that we're potentially overfitting. Now, to combat this, we can stop training before it gets to that point. So we can just cut the training off early. Now, there are two ways we could potentially do that. One of the ways would just be to manually stop at a certain number of epochs. But we can use a better tool, which if you came along to one of Mike's sessions, Mike also mentioned, called early stopping. And basically, early stopping is a nice feature of Keras that basically says, keep training, but check yourself against the validation set. And if you're not really getting any better anymore in the validation set, then stop. Don't keep going. You've probably reached the peak. And this is on the validation set, remember, because the training set, if we let it keep running and running, it would just eventually probably get to 100%. But that's not going to be any good for us because it'll be rubbish at everything else. So the early stopping allows us to make that judgment call automatically without having to try different epochs, for example. So let's have a look at how we do that, which is the same. If you saw Mike's session the other day, you'll have seen this. So I'll just talk about it briefly. Where is it? There we go. So after we compile the model, before we fit it, i.e. before we train it, I'm going to create an early stopping callback. So right at the very start, I've now imported from keras.callbacks early stopping, which allow me to use this feature. And then I'm going to set up this new callback, which is basically a meta thing that allows us to monitor and keep an eye on the training and adjust. So I'm going to set that up as an early stopping callback. I've called it early stop callback. And I'm going to pass in three things. The thing that I want it to keep an eye on, the minimum amount of change, and the patience level. So what this is saying is keep an eye on the accuracy level on the validation set. And that was the thing, remember, that we seem to be peaking early and not getting any better, which is an indication we're overfitting. Keep an eye on that. If the validation data doesn't change, the validation accuracy doesn't change by at least this, i.e. 0.01, the minimum amount of change, for this amount of epochs, so that's your patience level, so how long will you give it? Because it might sometimes just have reached a bit of a plateau, but it might then start improving again. So how patient do you want to be with it? I'm just going to set the patience level to 1. So if it within one epoch can't get better, then it'll stop the training there, which is quite a low patience level. But then we've only got 10 epochs here, so it's quite a low level. This is basically saying keep an eye on the accuracy of the validation set. If it doesn't change by this in this number of epochs, then stop. And then we can add that callback when we call the model.fit method. We can just add that as a callbacks equal, and we pass a list of callbacks we want to use. We only want to use one here, but we still have to pass it as a list. And we pass in the early stop callback. And now when we train the model, let's do it. I push F5. When we train the model this time, it should stop itself if it's not getting any better on the validation data. So we're on to epoch 2 here. Validation accuracy is 73%, 81%, 83.4%, 84.76%. Right, here we go. So it's not started to improve enough. There's not been enough of a change. It started to plateau where we thought it was plateauing. So it stops. So then it runs 6 epochs and then it doesn't go again. And so then it just cuts off and then it goes to the rest of the code where it looks at the test data set. So in this case, we've got down to about 84.5% accuracy, which is actually lower than we had before. So it doesn't seem to have done much to help us. But in some cases, it may well. So it's worth having that early stopping in there to try and make sure that you're not overfitting. Hasn't made a huge difference here. There's probably other things we're going to need to do as well. But it's a good first step to make sure you're not overfitting on the data. Okay. I want you to take a break. When you come back from the break, I'm going to get you into groups and give you this exercise to work on. I'm not going to give you quite an hour. I'm going to give you a little bit less. We're running a little bit over. Basically, what you're going to do is you're going to create a CSV file called ex1reviews.csv. And in that file, you're going to write a small sample, I mean small, like five rows of short movie reviews with a new review on each line. So these just make up some very short reviews, like 1 or 2 sentence reviews of something, and write about 5 of them. And then save that file in the same folder as wherever you've got your code. Then take a copy of the essay with own data early stopping, the one I've just run. And I want you to add functionality to the end of that code that reads in the reviews in the CSV file and stores them in a list. You don't need to do anything complicated there. That's just think back to your early Python training on reading in CSV files, where you're just going to read in things a row at a time and add them to a list. That's all you need to do. And then that will then go through that list of reviews that you've read in. And for each review, it's going to apply the exported model that we've trained earlier in the code to the review, so that it uses that trained model that we've just trained up here, that seems to be about 85% accurate, and see how well it predicts your reviews that you've just made up. And what it should do, or what I want you to get it to do, is print a copy of the review text along with the predicted sentiment for each review according to one of 4 categories. So if the output value is less than 0.25, then I want you to say it's a confident negative for this review. If it's between 0.25 and 0.5, a possible negative, possible positive if it's between 0.5 and 0.75, or a confident positive if it's between 0.75 and 1. And you should also print out the raw output value alongside that. Now, a couple of things to remember here. When you're reading in from a CSV, each row will be a list of comma-separated entries, even if the row has just 1 entry. It'll be stored in a list at position row 0. And to generate the bit I haven't told you yet, to generate predictions on new unseen text, we call the predict method of the exported model. So here, this is the file you'll be taking a copy of. So we've saved our new model that, remember we said that we've made this ready for just reading in text. We don't have to do all the vectorization, it'll do it all for us, because we've bunged that on at the start, and we've bunged on at the end the way we get out a number between 0 and 1. So we've called this export model. If you say export model dot predict and then pass it some text, it'll now use its learning to predict whether that text is positive or negative. That's all you have to do. And the way I do it, you can do it however you like. You can pass it, feed in a list of strings if you want. But I would do it by going through a for loop where you go through each review in your list, and then you call the predict method on that piece of text. Just beware that when you call the predict method model export model.predict, you have to pass in a list of strings. So even if you're just doing that and passing in 1 review at a time, you'll still need to pass it in as a list containing just that single review. So just be mindful of that. So that's all I want you to do for the code wise. Just add on to the end of the code that you're basically going to so write a CSV file with 5 reviews in it, and then add to the code so that it reads in those reviews and stores them as a list. And then you use the model.predict on the exported model.predict on each of those reviews in turn. And then you also get Python to say whether it's confident negative, possible negative, etc., based on the output value. So when you call model.predict, it'll output a value between 0 and 1, because that's what we've told it to do. We've told it to use a sigmoid activation function. So if you just call model.predict, it'll on a piece of text, it'll say 0.7 or something like that. So take that output and then convert that to print a message depending on where it falls in this range. So try that on your own reviews, see how well it works, and then play around with other aspects of the model. So try changing other things. Try halving and doubling the number of training epochs, changing the early stopping threshold and patience level. Add another hidden layer to the network. Change the number of hidden units in the hidden layer. Try changing the batch size, although be very careful if you do that, because if you make the batch size much bigger, your compute time will increase significantly because it has to stuff everything through at once. So unless you're confident in how to route that to a very fast graphical processing unit, don't do that. Just make small changes to the batch size. Try changing the training validation split. Maybe make the validation set bigger, so it's like 40% of the training set, or make it smaller. So see if you can improve the accuracy that you're getting on your reviews. And also try writing some mixed reviews. See how well it performs. Try writing things like, I thought the acting in this movie was great, but I thought the special effects were rubbish, or something like that. See what it does on something like that. So I'm not going to give you quite an hour because there's other stuff that I want to cover as well. So I'm going to give you just over 5 minute break, stretch your legs to 1/4 past, and then I'll give you about 35 minutes or so to have a go at this. This code bit shouldn't take you very long. This is actually quite easy. If you're not finding it easy, you've probably overcomplicated it. All you're needing to do is read in your CSV file, store the entries in the list, and then call export model.predict and then pass in each review. That's all you have to do. And obviously get it to, depending on what numbers output, print one of those messages. So it's all pretty easy Python, actually. The more interesting bit is I want you to play around with the model. The other thing to say, I don't know how well this is going to run on your computers. I have a very, very fast computer that is very set up for machine learning and runs very quickly. So you may want to just judge how well it's running on your computers, and whoever can run it the quickest may well be the one that you may want to screen share and do this, because and if none of you are able to run it very quickly, then think about reducing the number of epochs, because that'll help the training. Okay, so stay on the call, have a break for 5 minutes. I'll split you into breakout rooms now, and then when you come back 11:15, I'll give you 35 minutes or so to add that little bit of code on the end, and then have a play around with it. Try your own reviews, see how well this model works. Cool, okay, see you shortly.
Put in more negative responses to anything and everything than they do positives?
Depends on, so that may well be it. So for the, particularly for the IMDb, you'll probably get more people writing negative things about reviews, about films.
Yeah.
You have got the same number of negative and positive reviews in the data that it's been trained on, but of course there may be people that have written positive reviews but then also criticized it, and you may have fewer people who write a negative review who then write positive things. So it may be seeing more stimuli in terms of negative stimuli than positive. So that may well be part of the problem as well. I mean, so when we did some work with Derriford looking at their patient survey data, we actually had the opposite problem, that in fact overwhelmingly people were very positive about the care they received. And actually, if you think about it, that's kind of, if you ask somebody who's just come out of hospital about the care they received, they tend to speak very highly of the care, and they'll usually make some criticisms, but overall their judgment may well be very positive. So you'll have negative reviews in there, but we've found that the overwhelming majority were actually very positive. And that causes a problem because you need a good balance of people saying really bad things as well. And if you haven't got enough of that, then you can end up biasing your training, because you can end up, so let's say you had trained on 100 reviews and 99 of them were positive and 1 of them was negative. The neural network can learn to just say everything's positive. Doesn't matter what you feed in, everything's positive, and it would be right 99% of the time on the training. So you have to be very careful about the balance of the training that you're putting in, that you're not including a bias. So obviously here we've included an equal number of positive and negative, but you're right that there could be things in the negative reviews or even in the positive reviews that are a little bit more negative leaning or positive leaning, and there may be an imbalance there that's causing a problem. So that's, you have to be really sort of mindful of the data that's being fed in, because it will pick up on all sorts of things. And a particular challenge that we've just looked at, if we consider this as an example review from a patient survey question, what did you feel about your stay in the hospital? Would you rate this as positive, negative, or neutral, and why? So let's imagine the patients put the care from the staff was absolutely fantastic. They made me feel safe and nothing was too much trouble. But when I was discharged, I had to wait over 5 hours for my prescribed medications at the pharmacy. This is atrocious. So how would you rate that? If you had to say, is that positive, negative, or neutral, what would you say?
Negative, to make something happen about the bad bit.
It's a
Interesting.
positive review about the stay in hospital, and then they've added an additional review about the pharmacy.
Yes, back to that. So there's a problem here because there are clearly positive and negative elements to the review. So if we were to consider the overall review as positive, then essentially what we would be doing is making the assumption that the care from the staff was more important to the reviewer than the wait at the pharmacy. Now, that may well be true, but we don't know that. So we're then impressing that assumption. If we were, on the other hand, to rate it as negative, then we're assuming the opposite, that the wait at the pharmacy was more important than the care they got from the staff, which again, may be true, but we don't know that.
I suppose that's my experience was that it was heart medication and it's supposed to be taken every 4 hours, and it was actually had that happen. And it was the time when you were supposed to have taken the damn stuff. So
yeah.
Very good for my dad.
Fine, I see, yeah, absolutely. And so you may have...
But also you do want to deal with the problems. The positives are great, but you can't leave the negative. So if you only had an option of all of it in one and it was positive or negative, to me, to actually address that issue is the important bit from what they've said to us.
Yeah,
you'd almost want to split it into themes, wouldn't you?
You would.
One about pharmacy and one about the in-hospital stay.
Well, funny you should say that, Heather.
Oh,
might be exactly what we're going to do. What we're going to do. So clearly, we can't rate it as just positive or negative. There are issues with that. And if we rate it as neutral, then that might seem like a good sort of get out of jail free card. But in fact, we're making an assumption there as well, because by saying it's neutral, we're saying essentially that both aspects are weighted equally, such as their overall feelings are neither positive or negative. And that's highly unlikely to be true, actually. So what can we do? And there are two primary solutions. Now, one approach is that you can have sentiment analysis where you have a dual output, so that you don't just predict whether something's positive or negative, you can predict whether it is both positive and negative at the same time as well. You can have essentially two neurons at the end of the output layer. And that's fine, and that might be, if you're just trying to essentially use your AI to work out how many positive reviews, we've got 100,000 reviews, churn them through the AI, how many positive and how many negative have we got? That would work great. But in reality, I would hope normally you're doing this because you're hoping to improve something. And so the other approach, which is a little newer, is to break down the review into individual aspects. So it might be in the review we just looked at, we have the aspect of the care from the staff and the wait at the pharmacy. And rather than looking at the review as a whole, we can break it down into those aspects and then analyze the sentiment of those individual aspects instead. And this is something known as aspect level sentiment analysis, which is a slightly newer area of sentiment analysis. As I say, both areas are valid, depends on what you want to do, but typically for the kind of problems you'll be looking at, I suspect the aspect level stuff will serve you better. So a key difference with aspect level sentiment analysis is that we have to first split our text into different aspects. Once we've done that, we can just do sentiment analysis in the same way that we've just done. But it's that way of being able to split up the text into the different things that people are talking about. So consider this following paragraph. What would you say are the individual aspects in this text? So I tried to get through using the supply telephone number first, but nobody answered after 10 minutes, so I gave up. I then decided to go to the surgery in person, but I was waiting for ages here too. The receptionist I eventually spoke to was very rude. When I finally saw a nurse, she was incredibly helpful and put my mind at ease. I thought the coffee from their coffee machine is excellent too, makes a change. What would you say the aspects of this review are?
Got telephone waiting time, surgery in-person waiting time, quality of the receptionist, quality of the nurse, and then quality of the coffee machine.
Yes, exactly so. So there's 5 aspects that we've essentially identified here. So the wait, trying to get through on the phone, the wait.
Quality of the coffee ought to come first.
Yes, yes. These may not be in priority order. the rudeness of the receptionist, helpfulness of the nurse, and the quality of the coffee. So we can see that quite easily. If we were to read that, we can pick that out. But we need to get a machine to be able to do this, because we can't sit down through 100,000 reviews and pick out all the different aspects so that we can feed it into our AI. It's going to take too long. So how might we find these aspects automatically? Well, one option might be to look for our good old friends, noun phrases, which we talked about on Tuesday and also in the very first session. Noun phrases, also known as noun chunks in natural language processing. So remember that noun phrases are phrases that have a noun as their head. So you have the noun and the words that describe that noun or modify that noun in some way. So you may have the cat or the fluffy cat or my cat. These would all be examples of noun phrases. So I just want you for the next 2 minutes, stay on the call. I just want you to just write down what you think the noun phrases are in this paragraph that we just read out. So I'm just going to give you a couple minutes just to jot some ideas down, and I'll ask somebody to share their thoughts. Okay, has anybody managed to do that?
Yep.
Okay, do you want to share what you think the noun phrases are?
Well, I've put the chat, but essentially we've got telephone, as in the supplied telephone, surgery, receptionist, nurse, that's a nurse, not the nurse in this case, and then coffee and the coffee machine.
Okay. Anybody have anything different?
I thought the noun phrase for about the coffee was the coffee from the coffee machine. It was all one.
Mm-hmm.
Yeah.
Yeah.
Should we have the time in there, the 10 minutes? Minutes?
Let's have a look. So these are the noun phrases in that paragraph. So we've got the supplied telephone number. The number is the head noun, and these are the words that modify that noun. What type of number? It's a telephone number, and moreover, it's the one that was supplied. So it is the supplied telephone number. Nobody answered after 10 minutes. Yeah, you're absolutely right. That's a noun phrase. The noun being minutes. How many of them? There were 10. The surgery, obviously fairly self-explanatory. The receptionist I eventually spoke to is a noun phrase. The receptionist being the head noun, and then it's the one that they eventually spoke to. A nurse, explanatory. My mind is self-explanatory. And then you're right, the coffee from the coffee machine. Coffee being the head noun. Could also arguably, though, be the coffee. No, actually, it would be the coffee. The coffee from the coffee machine. Which coffee is it? It's the coffee from the coffee machine. So semantically, that's the head noun. That does go back to the point, though, that there are other nouns here, and so we have to be very careful when we're training a machine that it doesn't pick this up as being the head noun instead. So let's compare the noun phrases we identified with the aspects we identified. So we've got these as our noun phrases, and we've got these as our aspects. And actually, it's not a bad match. It's actually picked up on the main aspects we're talking about, the telephone, about the bit about the surgery, the bit about the rudeness of the receptionist, the bit about the nurse, the bit about the coffee from the coffee machine. So by finding these noun phrases, we seem to have found the bits of the review that match up to the aspects. Largely, we found some extra bits as well, but we've largely managed to find the aspects that we want to split it down into. Now, so if we can use noun phrases as a kind of first approximation to try and maybe break this down into aspects, what we could do is look for noun phrases and then apply sentiment analysis to the sentences which contain those noun phrases to see if we can do aspect level sentiment analysis in that way. Now, we can look for noun phrases really easily because Spacey has built-in functionality to do this. When we run when we saw on Tuesday, when we run article equals NLP and then we stuff in our raw text, as well as doing all the named entity recognition stuff for us, it's doing all the rest of the things. And I alluded to the fact on Tuesday, it's doing lots of other stuff in the background as well. And one of the things it does is around parsing, and it does a process known as chunking. And chunking is where it identifies the semantic chunks in a piece of text, including identifying noun chunks. And so just by running that single command from Spacey, you can then access all of the noun chunks in your text just by saying article.noun chunks, and it will give them back to you. So let's look at a simple example of how we might do that, and can it improve the quality of the sentiment analysis for this review, which was the 6th review I put in, which was the acting was great, the special effects were rubbish, which is clearly a mixed review. And there's clearly two aspects here. There's one about the acting, which was great, and there's one about the special effects, which were rubbish. So if I go into code, here's one I made earlier. I'll scroll right down because all of the code at the top is all exactly the same as we had before, but we're just going to add some extra stuff in now. And we're going to use Spacey, so we've imported Spacey to do this. So as we saw on Tuesday, we're going to load in the pre-trained model. So I'm just going to use the NCall WebSM model here, but you may want to use some of the larger models if you were doing this outside of training. We're going to set up a dictionary which stores the noun chunks from each review. And I'm going to have a review index so that I can store each list of noun chunks against a review number. So I know that list of noun chunks belongs to that review, that list of noun chunks belongs to that review, etc. And then basically what I'm going to do for each review, I'm going to apply the Spacey pre-trained model, the NCall WebSM model, which will, part of what it'll do is grab some noun chunks. It'll tell us where the noun chunks are. And then I'll grab those noun chunks out and I'll add that to the list of noun chunks for that review. So that's all I'm doing in this loop. I'm looping through all of the reviews. These are the 6 reviews that we read in. So I'm going to apply the Spacey NLP model to it. And then I'm going to set up a little list, a temporary list here. And then it'll go through for each of the noun chunks. I'm going to append that noun chunk to that little temporary list. And then I'll append that final list once I've got all the noun chunks for this review. I'll put that in my dictionary of noun chunks, and I'll store that against a key of the review index. So the first review will be review 0. So it'll store against review a key of 0 in that dictionary. It'll have a list of the noun chunks that Spacey found for that review. Then it'll increment the review index by 1 and go around and do the same for the next review. So we'll build up a dictionary where the key is the review number, and then the value is a list of all of the noun chunks that Spacey found for that review. That's the first step. Then we'll just go through each of the reviews again in turn, and we're going to print out the identified noun chunks. But more than that, we're then going to split the review up into sentences, and we'll look for that noun chunk in those sentences. And if that noun chunk is found in that sentence, we'll then apply the sentiment analysis model to that. So if we have a look here, we're going to go through all of the reviews again. We reset our counter to 0 in our reviews. First of all, we're just going to print out, here are the noun chunks that were identified for that review. And then we're going to tokenize by sentence. Remember I said right at the start that you can, as well as tokenizing by words, you can also tokenize by sentence. And so you can use the sent tokenize method to do that, which basically just splits your text up into individual sentences. So in our review that we're looking at, I haven't got here, but we've got a 2-sentence review, so it should split it up into 2 sentences. So for each sentence in that review, and then for each chunk, each noun chunk that you identify for this review, we're going to see if that noun chunk is in that sentence. And we can just use the in keyword to do that. So we say, is that noun chunk you identified, is that in this sentence? If it is, then we're going to do this. If it's not, we'll just move on and check the next one. But if it is in that sentence, then what we're going to do is we're going to predict the sentiment of this sentence by calling the export model.predict method, and we'll pass in the text just as we did before, but it's just going to be the sentence this time instead of the whole review. And we'll apply the same logic that we did before, that will say if the output score is less than 0.25, then it's a definite negative, possible negative, etc., etc. Let's run that. Let's see how well this will now work, because we had a couple of mixed reviews in there. So it'll be interesting now to see if this gives us more information by just using a pretty simple approach. We're just basically breaking down the sentence into the review into noun chunks, and then looking for those noun chunks in each of the sentences. And then when we find that, we say there's an aspect here, and we'll apply the sentiment analysis just to that sentence. Let's see what happens. Let's look first at the final review, review 6 or review 5, because we start counting from 0. This was the problem one. So remember, the sentence was the acting was great, the special effects were rubbish. Before, it said it was a likely negative, but it was about 0.46. Now, it's identified there were 2 noun chunks here. The acting, and that was found in the sentence, the acting was great. It's predicted that sentence to be possible positive. Again, it's still being a bit more cautious on the positive, but it has classified it as positive because it met the threshold, and it's gone over the 0.5. So it's predicted that with 0.54. The special effects, it also picked up as an aspect, and it picked that up in the sentence, the special effects were rubbish. That sentence is predicted to be negative, and it's got an output value of 0.44. So we've now turned that review from being our output from being, we think this is a possible negative, but not very strongly, to being, we think there are 2 aspects to this review, something about the acting and something about the special effects. And the acting, we believe, was reviewed positively, and the special effects were reviewed negatively. So we've managed to break that down. So now not only do we know whether the review was positive or negative, we know what aspects of the review were positive and negative. Now, in reality, you may need to do some slightly more fancy things, because you may well have duplicate noun phrases found in multiple sentences, for example. So you need to think about how you might sort of cleverly do this. But the point is, by using noun chunks, you can start to break down your review automatically to try and find out what some of these common things are. And of course, because we've now got these aspects, such as the acting, the special effects, we could then look over all of our reviews, if we had thousands of them, and say, okay, if we look at the acting, do people tend to talk about the acting positively or negatively? And if we then think about how we then apply it to our domain, so if we were looking at our patient survey, we could then say, okay, here are the things that people have been talking about in the reviews. One of the things is the pharmacy. And it seems most people are talking negatively about the pharmacy. So maybe we need to look at what we need to do about that. And we can look to see what are the aspects of the pharmacy that are being talked about. And we can use other methods, such as the topic modeling and the named entity recognition, to see, are there certain names that are coming out. If we're looking over multiple organizations, it might be there's different pharmacies that are coming out in these negative reviews. So we can use these different methods to try and drill down into what is it that people are talking positively about and what is it that people are talking negatively about. So moving just from having this, we've got 60% of our reviews are positive. Great. But actually, of the 40% that aren't, what are they talking about? What are we getting wrong? And this kind of approach, and this is just really simple first cut, but already it's given us some quite effective results that allow us to then break our text down further to try and work out what is it that's positive and what is it that's negative. If we look at some of the other reviews, this was classified as a positive review anyway, and it's picked out 3 different chunks here. So I is obviously one of those, so you may want to think about, if you were doing this, how you might want to get rid of some of those almost meaningless noun chunks. The aspect here is about the film. That's more closer to what we want to look at. That's predicted to be positive, but so this won't be a sort of cure-all for it, but it will start to nudge you in the right direction. And there's a lot being done around aspect level sentiment analysis at the moment to try and see how we break down text into different aspects so we can better get more useful information, hopefully, out of sentiment analysis. Okay, any questions about any of that?
I presume you could use essentially an extended dictionary to strip out sort of aspects like I and the like.
Yeah, absolutely. So once you've gone through, because all we've done here is basically said, give me chunks, and then I'll take those as my aspects. But yeah, you're right. You could, if you were doing this in reality, you could then say, okay, I've now found all the noun chunks. Now let's start to intelligently go through and see if there are meaningless noun chunks, and can I apply rules to get rid of meaningless stuff like I, or so remove anything as a pronoun, it's just a pronoun or something like that. So you could then start to build up your rules for how you start to eliminate noun chunks. Hopefully, you're then getting to a position where the remaining noun chunks are closer to the actual aspects that you want to look at. You could even combine it with named entity recognition. So if you wanted to specifically look at the way people felt about named people, for example, you could apply named entity recognition to pull out the named entities that are of type person, and then look for those, and then use that to identify the sentences that you will be analysing your sentiment on, or a combination. So there's lots of different ways in which you combine all these methods, essentially, to try and better sort of hone down on what you need. And part of it will depend on what you want to do, and part of it will depend on what your data's like as well.
With the chunks, Dan, when you need to have a lot quicker computer in the end, effectively, because when you're doing those words and you sort of assess how many times the word appears and the rest of it, it's all quite simple and broken down, but you're so unlikely to have a duplicate noun chunk, however hard you try, that it's going to take a lot longer to process it all, surely?
Sorry, do you mean for things like removing the duplicates? Do you mean, sorry?
Well, no, the first method we looked at, where we were looking at words rather than noun chunks, weren't we, the first time around?
Yeah.
If you're using noun chunks, they're not going to take place more than once ever, are they, really? So you're going to have to, surely it's much slower to work through them.
Well, they might, because if you look at the, in fact, they probably will, depending on what your noun chunks are. So, things like here, the acting and the special effects, those noun chunks in movie reviews, for example, you'd expect to see probably that quite a lot, because a lot of people would say something about the acting or the special effects. And the same with some of these potentially redundant noun phrases where you've got, just a pronoun or just the word I. But as Greg said, you probably want to filter those out first.
Yeah.
I mean, you can do a lot of this.
You think you would get enough? You would get enough of.
Yeah, I mean, it depends on your. I mean, you could try it without, and then gradually building the filtering process. What you'd probably want to do is be intelligent in the way you make your code more computationally efficient as well. So here, for example, you may want to break out once it's found a noun chunk and say, okay, I've done that, rather than going through and looking through all the rest as well. It doesn't matter if this example is small and computationally efficient, but if you were building that up, you'd want to think about, and this goes for any code that you're doing, you want to think about, once you've got a working program, what are the ways in which I can make it more efficient? Are there things that I'm doing that I don't need to do, they're just taking up computational time? But normally you do that as a sort of iterative process. You gradually make more and more efficient versions of your code. And sometimes you just cast the net wide at the start to see what comes out, and then see if you can then sort of further refine it down. But there's definitely ways you can make all of this much more efficient. The nice thing about using something like Spacey, though, is of course, all the noun chunk stuff, that's all using a pre-trained model, so you don't need to go through the training for that. You can Spacey can very quickly grab you out noun chunks, even on thousands of sentences very quickly, because it's pre-trained to do so. And similarly, once you've trained up your sentiment analysis model and you've got a good model, you can then just apply that model very quickly using the predict, and it can very quickly apply those weights. All it's doing is feeding through, turning your text into some numbers, feeding that through the pre-trained weights, and then coming out with a number at the other end. So it actually does that very quickly. But yeah, there's always ways you can make this more efficient, and that's an important part of the programming process.
And how would you deal with the idea of balance in all of this? Because presumably, I mean, in that review, somebody had an impatient state, you know, the pharmacy example. Mm-hmm. So they had an impatient state and they had a negative experience with pharmacy, but presumably there's a lot more reviews where they haven't had a negative experience with pharmacy, so pharmacy never gets mentioned at all. So if you're only picking out the ones...
Right, yeah, so you'd need to think about not just this was an aspect that somebody talked negatively about, so we say this had 100% negativity around the pharmacy, but it was just, as you say, because, you know, the other 9,000 people didn't talk about it. So you'd probably also want to not just report on, you know, the percentage of people that are talking about something positively or negatively, but also the number of people or the percentage of the your data set that are actually mentioning that, to see how representative that is. And you may even want to pre-filter some of that. So actually, if you've only got one person talking about the pharmacy out of 10,000, it's probably not that useful. It's just one person's thoughts on the pharmacy. That doesn't really give you much information. But if 500 people are suddenly all talking about the pharmacy and most of them are talking negatively, that might give you some information that's useful. So yeah, absolutely, you'd want to, and again, that could be in your noun chunk sheet as well. Here we've just done a very, you know, simple, grab me all the noun chunks and I'll go through and look at everything. But you might, after you've identified the noun chunks, say, okay, how many times do these noun chunks come up? And I'll set a threshold so that if fewer than 4 people talk about these things, then I'll eliminate it. And we won't look at that at all. So it's all part of the design process, really, how you want to look at that, what your data looks like, how much data you've got. But obviously, the more data you've got and the more balanced it is, at least in terms of people talking positively and negatively, better. But do remember, as with all supervised machine learning, which this is an example of, where you're essentially training them on examples where they know the answer, so that they can then get good at predicting where they don't know the answer. Remember, you've got to manually specify whether all of these reviews are positive. If you want to feed in 1,000 reviews to train it on, that's great. But you're going to have to sit down, or get somebody to sit down and determine whether those reviews are positive or negative manually. And that's a further complication with aspect level sentiment analysis, because strictly speaking, if you're then going to validate that, you'd have to get somebody to break it down into the aspects and review those positive. Because if you're going to check to see how well your model is doing, it needs to see examples of that. You can get away with it with the aspect level stuff a little bit, as long as you're confident that your outer model, your general model at picking up reviews, you know, the review level is good, because, you know, something like this indicates that it's actually, once it's able to do a review quite well, it's pretty good at predicting sentiment of sentences. It seems to be getting these right. So that seems to be good. But you, at the very least, remember, however many reviews that you pass in, you're going to need to be able to give it the answer for those number of reviews. Not just for your training set, but also for your testing set, the set that it sees after. So bear that in mind before you go saying, I want 10,000 reviews in training.
Two questions, Dan. One, I presume if we were doing sort of targeted, we wanted targeted sets, so say it was, you know, a hospital, and we wanted to go, we really care about the pharmacy and the nurses and the receptionist, but they're the only bits we're looking for, then we could then put in a filtering layer against sort of those dictionary nouns.
Yeah,
and then
absolutely.
Say only predict these ones.
Yeah.
And the other one would be if we know if we're seeing that we run our test data that it's good at predicting negative and bad at positive. How would we go about giving it more information to be able to be more accurate with our positives,
So
without then biasing what we've done?
So that's a tricky question. So it depends on why it's doing that, which you may not know. This is where the trial and error art form of machine learning comes in, and it is very trial and error. You can get one of these things set up really quickly and easily because they all follow the same sort of structure, but then actually refining it to perform well is where the real art comes in, because it might be that it's just a case that you need to give it more data. So more of it might be that your your negative data actually contains a bit too much positive information in there as well, and it's biasing one way and the other. So you could just give it more of the other to see if it can train better on that. That's the easy solution, but often that isn't the case. And sometimes you just need to restructure your network. Is it that you're training it for too long? Is it that you're the way you're batching up your data and sending it through, is that wrong? Is the structure of your network wrong? Do you need to think about the way you've got your layers set up? Are you overfitting? Are you underfitting? All of those kind of things that you need to think about, and it is very much trial and error. So there's general advice out there in terms of what people have done in terms of things like using global pooling 1D layers to squash down so that it reduces overfitting, using the dropout layers. These are sort of common conventions that are adopted, but there's still a lot of flexibility in terms of how you build these things up, and also how you parameterize them. And there's no right answer. It's you've got to find what works for your data, and that's why you need a good training set. And then you need a good test set so you can get a good sense about how good this thing is that you've trained, so that you can be confident that you've trained a good model. Then when you give it on completely brand new data, that you're more confident in its results. But it is an art form. It's and that's part of the fun, I guess. If that doesn't sound like fun, then machine learning may not be for you, because that's a lot of where you have to sort of play around with stuff and see what happens. But because actually, it will take a while for you to get to understand all this. But actually, this structure, as you've already seen, is fairly similar to the things you've seen Mike talk about. I mean, they're all very similar in terms of their structure. So you'll soon get the hang of how to build a neural network if you do them enough. But it's the playing around with stuff to get it working for your data that's the real trick. Great. I think we'll break there because I know Tom's got to start very promptly at 1:30. So if you're going to the session at 1:30, you'll want a nice lunch break. So thank you, everyone, for coming on this morning. And thank you this is my last session on the course. So hope you've enjoyed the training. And it's been a pleasure teaching you all. I've said it before, I'll say it again, you've come so far since the beginning of October to now be doing this kind of stuff from where you were. Is phenomenal. So a big pat on the back for all of you. And I look forward to seeing what you guys do with this in the project work in phase 2 when we start in January, because it'll be really exciting to see how you're going to apply some of these skills. And I know a lot of you doing some natural language processing in bits, lots of you doing discrete event, geographic modeling, machine learning, lots of stuff in there. So you get lots of chance to practice all this and see how it works in the real world for your systems, and see what comes out of that. So great, thank you all. And if you're coming along to Tom's session this afternoon, starts at 1:30. There's a Zoom call that starts and end, so make sure you join for that. And Tom's going to be this afternoon doing forecasting, but looking at some cutting edge methods using neural networks, which if you've attended this morning, hopefully you'll be a bit more well versed in. Fantastic. Thank you all, and have a nice lunch.
Thank you, Dan. Thanks for everything.
No problems.
Thank you.
Cheers, Dan. Thanks. Bye.